All right, here we got section 4.5, exponential growth and decay. Woo! You guys back and ready for section 4.4? That was a long one. This one's going to be short. I know you're excited. All right, let's dive right in. All right, here's the basic formula that we're going to be looking at for the entirety of the exploration for this section. All right, so this looks very similar. This kind of looks like the continuous interest formula, because really it kind of is. So let's take a look at each of the parts here. Okay, first part, a sub 0. That just means the initial population. In the continuous interest formula, this is the principal amount. It's the same idea. What do you start with? How much do you start with? Then we've got K. K is the growth rate. Remember that percentages are always going to be written as decimals. I cannot stress this enough. This is where the majority of mistakes that I see happen. 7% is 0.07, not 7. That's 700% if you write it as a 7. T, of course, is time in years, which leaves us with the last one, A, which is the amount after the growth or decay. Okay, so how do I know if it's growing or decaying? If k is greater than 0, then the function is growing. If k is less than 0 or negative, it's decaying. And most importantly, when time is equal to 0, a sub 0 is the initial population. So t equals 0, or time at 0, is the population at the beginning of when this function measures the growth or decay. So let's dive right into some population analysis. So in 1990, the population of Africa was 643 million. By the year 2000, it had grown to 813 million. This is a two-part question, so I have to find the exponential growth function. And then when will the population reach 2,000 million, or 2 billion people? All right, first part, we got to solve for k. That's what we really need to do to rewrite the exponential function. Now, t is equal to 10 years. How did I get 10 years? 2,000 minus 1990. 10 years. We have the initial population of 643, and we know that the new population is 813. Awesome. Okay, I can substitute all of that information in, and the only thing that's missing is the constant of growth or decay. So I need to isolate, just like we did in the last section. I'm going to isolate and find the value of k by isolating e and k in the exponent. So I'm going to divide each side by 643. Because I have e to the 10k, I need a tool to take a variable out of the exponent, which of course is taking the natural log of both sides. Take the natural log of both sides, which means ln of e to the 10k is just 10k. This allows me to divide each side by 10. I know this looks gnarly, but remember, all of the heavy lifting is going to be done in the calculator, your graphing calculator. And you can type this in exactly as it is written on your paper. And that equals about 0.023 or 2.3%. So that lets me rewrite the exponential growth function for this population analysis problem as a is equal to 643 e to the 0.023 times t. And since we know that k is positive, we know that population is growing. All right. Second part of the problem asks me to solve for time. It says, when will the population reach 2,000 million? So I know that a must equal 2,000. All right, this is going to use what we saw here, and I'm just going to rewrite this equation into directly just the ln like we saw here, because the only thing that's different is that we're solving for t, which is the same place. All right. So now that we're here, our calculator does the work, and that we know that it's about 49.3 years after 1990. Well, 49 years after 1990, that's 2039 that the population will reach 2,000 million or 2 billion people. We're not that far away, people. So another way we can analyze this is by using what we know as the half-life of certain elements. So if I know that the half-life of an element is 28 years, I actually don't need to know how much of that element I have. So I can rewrite the exponential growth function, a is equal to a sub 0 e to the 28k, because time is 28 years. Now this is finding k, or the exponential, the rate of growth or decay. After 28 years, I know that the amount left has to be half, or the initial population, a sub 0, divided by 2. So I can rewrite the equation. All right, I don't like having multiple variables here. The only variable I want is k. So I want to get rid of this a. So a sub 0 times e, that means I can multiply by the reciprocal. And a really cool thing happens. When I multiply 1 over a sub 0 to the left-hand side of the equation, that a sub 0 cancels out. You see 1 in the numerator and 1 in the denominator, which means I just ended up with 1/2 is equal to e to the 28k. Bonkers. Because now I can just take the ln of both sides, the natural logarithm, and we know that by taking the natural log of e to the number, I'm just left with the exponent. Solve for k, and k is about negative 2.5%, or negative 0.025. Awesome. Okay, so we can apply this, and doctors apply this using logarithmic disease models. All right, this is gonna be slightly depressing, but p of t, 90 divided by 1 plus 271 e to the negative 0.122t. This equation, this logarithmic disease model, models the percentage p of x, or p of t, sorry, of Americans who are t years old with some coronary heart disease. Yeah, so we all have some measurable amount of coronary heart disease, and this measures that percentage. So, three-part question. This is going to wrap us up and take us home here. What age is the percent 25? The second part is, what age is it 50%? And then I want to know the limiting percentage. Okay, each of these bit by bit. What age is the percent 25%? So I'm going to actually substitute and say 25 is the p of t. All right, this is ugly. I got to multiply here. If I multiply by the denominator, it's going to cancel away the denominator. So I have to distribute. 25 times 1 is going to give me 25. 25 times 271 is going to give me, I think, 6,775. And that will cancel on the right-hand side. So kaboom. Yes, 6,775. So 25 plus 6,775 e to the negative 0.122t is equal to 90. Again, because on the right-hand side, these just cancel. And I've distributed 25 times what's in the green here to get the left-hand side of that equation. All right, so now I can actually start isolating for the variable, which is in the exponent of e. All right, so let's isolate e. So I'm going to subtract 25 from each side, leaving you 65 over here on the right-hand side. I'm going to divide by 6775. And of course, if all I'm left with is e2 and an exponent, I can take the natural log of both sides. And after I've taken the natural log of both sides, I can just divide to find how much time. That's 38 years old. As I record this video, I am 37. So there is a 25% chance that my peers who are 1 year older than me have, there are 25% of them that have coronary heart disease, or some measurable percentage of coronary heart disease. All right, so I want to pause the video here. Well, I mean, I'm going to not advance the slide and see how, again, I think the biggest leap that I made was by multiplying by the denominator. And the key to solving this was seeing that the 25 is not a percent as a decimal, it's just the number 25. All right, so at what age is it 50%? I'm going to actually let you guys solve this one on your own. So go ahead and pause the video. I'm not going to have the work written out because it's literally exactly the same as this work here. It's just changing the 25 to a 50. So solve it on your own. I'm going to pause. Come back when you're done. Did you get 48 years old? Yes. If you got 48 years old, you are absolutely correct. If you are 48 years old and you live in America, then there is a 50% chance that you have some measurable amount of coronary heart disease. This is not a very positive topic, but yes, that is absolutely true. So, the third part about this logarithmic disease model is what is the limiting percentage? So, what the heck do I mean for limiting percentage? Limiting percentage occurs as we put time to infinity. So we're going to push time to as the oldest possible time that it can possibly get. So I want you to yank out your calculator, and I want you to take just this part here, e to the negative 0.122t, and I want you to plug in larger and larger values for t. As you do, you should see that as t approaches infinity, e to the negative 0.122t approaches 0. Now, this is extremely important and verging on a calculus topic, but it is awesome because now the function p of infinity becomes this. All of this nasty e to the negative 0.122t turns into the number 0. 271 times 0, that's 0. 1 plus 0 is, the limiting percentage is 90%. So 10% of the population of North America or the world, however that function was created, will never have any form of coronary heart disease. Awesome. We're good. Ladies and gentlemen, compared to our last exploration, this was short and sweet. Make sure that you review the video as needed. And this is some really cool stuff. I love doing population analysis. So make sure you understand all the parts of this exploration as we move forward. Excellent. That's been section 4.5, Exponential Growth and Decay, with me, Mr. Hayne.